So far, with all of the equilibrium problems we've been doing, we've been able to write out our expression for the equilibrium constant, plug in what we know, and there's only been one piece that we needed to solve for, so we could just rearrange and solve for that missing piece. Unfortunately, sometimes that's not the case. Sometimes we plug it in and we find that there are 2 things missing from the equilibrium expression, or 3 things missing, and we don't know where to solve from there. If we ever come to that, what we need to do is use what's called an ICE table. The general form of these is that you have all your reactants and products listed up top, and then you make 3 rows. One for initial concentration, what you started with, one that represents the change in your concentration during the course of the reaction, and the last one is the concentration at equilibrium. So ICE, that's where we get our ICE. So what we're going to do is follow the same procedure we've been following before. We're going to write out the expression for the constant. We're going to plug in everything we know, and if we can't solve right away, we're going to make an ICE table. After that, there should just be one piece left that we need to solve for. Now, there are 2 main ways these can shake out, so let's look at examples of each. First of all, consider the following reaction. If we start with 1 molar of A and have 0.75 molar of A at equilibrium, what is Kc? All right, first step, we write out the expression for Kc. Products over reactants, so we're going to have B squared over A. All right, plug in the information we have. So we don't know Kc. We're solving for that, so can't have that. Doesn't mention B anywhere, so can't have that piece. Now, there are 2 numbers for A, but notice since this is an equilibrium expression, only the thing at equilibrium can go in there. So since we had 0.75 molar of A at equilibrium, that's the number that's going to go in here. So we've plugged everything in, and now we look at it and we see, there are 2 things I don't know. I can't solve this problem yet. That's when we're going to break out our ICE table. Now, I just like to make them directly under our chemical equation. So right under our chemical equation, I'll write my ICE. I'm going to start out by filling the information I have. So I start with 1 molar of A. That must be my initial. B is a product. And if it doesn't mention how much product you start with, you can basically just assume that that's going to be 0. Oftentimes we only start with reactants. So we've used that piece, we've used the 1, we filled in B, and we know that we have 0.75 of A at equilibrium, but we don't know B. So anytime we don't know a number, our favorite way to represent it is as the letter X, and that's what we're going to do. So with our change row, we're going to just say, okay, I know I've going to use up some of A to make B, and I don't know what that is, so I'm just going to call it minus X. Negative because I'm using up A to make B, and X because I'm not sure what that number is. Meanwhile, I have to have made B, so I'm going to add here, but notice for every 1 A, there are 2 B's. So however much A I used up, I have to make twice as much here. So I'm going to put plus 2X. Now, I didn't have anything in the equilibrium spot for B, so all I have to do is add up the I and C rows, and they should give me the E row. So 0 plus 2X gives me 2X. So now I'm going to look back and assess. Notice that for A, I have an initial and I have an equilibrium value. That means there's only one unknown in this whole line, or this column, so I should be able to solve for X. So again, if you add up the I and C rows, it should give you E. So if I take 1 minus X, those are my I and C rows, it should give me my E row. And now we can clearly see what X is. Okay, 1 subtracting X gives me 0.75, so X must be equal to 0.25. So now that I've solved for X, I can go back to my equilibrium row and say, oh look, B is equal to 2 times X, so 2 times 0.25, so B must be equal to 0.5. And if I had other columns, I could fill those in too. Now that I've found X, I can finish completing my ICE tables and get numbers for my equilibrium row. Once I have my numbers for my equilibrium row, I'm going to go back to what I started with. I have my Kc expression, B squared over 0.75, and now I know that B at equilibrium is 0.50. So I have 0.50 squared over 0.75. Oh, so easy. I can just plug it into my calculator now, and I see that Kc is equal to 0.33. So again, We wrote our expression. That was step 1. Then we plugged in the numbers. That was step 2. And we saw that we couldn't solve right away. There was more than one missing piece. So we went over here and we made our ice table. And after we made the ice table, we noticed that we had one column where we only had one x. We had an initial value and an equilibrium value, so it was only this middle piece we didn't know. So we were able to solve for what x is, and then we took that and plugged it back in to solve for b. After we had a and b, we could plug it back into my expression and get the number for Kc. This is one way we can see these problems. Let's look at another. Wasn't sure if I needed more room. I didn't, so we'll skip past that. Very, very similar looking problem. Consider the following reaction. If we start with 1 molar of A and know that Kc is equal to 0.33, what are A and B at equilibrium? We say, okay, has to do with Kc. We're going to start the same way. Kc is equal to B squared over A. So first step, we write the expression. Second, so that's step 1. Second step, we plug in what we know. We know Kc is 0.33. B is never mentioned, so we must not know that guy. Now it says start with 1 molar of A. That's not my A at equilibrium. It's asking for A and B at equilibrium, so I must not know that guy either. So I don't know A or B. I can't solve right away because there's 2 things I don't know. So I go back and I make my ice table. So I say, all right, couldn't solve right away. I make my ice table. I'm going to fill in what I know. I'm starting with 1 of A. It doesn't mention B, and it's a product, so again, I'm going to assume that's 0. And that's it. That's all the information it gives me. So change again. I say, well, I'm going to use up some A, so I'll subtract x. I'm going to make some B, and for every 1 of A, there's 2 B's, so I'm going to put 2x there. So we always plug that coefficient in with our x. And now we just have to fill in these equilibrium rows by adding these together. So 1 minus x just gives me 1 minus x for A. 0 plus 2x gives me 2x for B. So again, I just took these 2 rows and added them together to give me my equilibrium row. I can't solve for x yet, because if I look for each of my columns, I have x in at least 2 rows. So there's no way I'm going to be able to solve for x in this case. So I'm just going to have to take these and go ahead and plug them back into my expression and see what I can do from there. So I have 0.33 is equal to 2x squared over 1 minus x. So you say, all right, I guess I'm just going to have to go from here. If I look at it now, I really only have one variable. There's only one thing I don't know in this expression, which is x. It's just not that easy to solve for, but I can solve for it. That's fine. So now what I'm going to do is just continue and do some algebra, which is not our favorite, but I'm just going to rewrite. Oops, didn't mean to do that. Rewrite this expression down here. So we had left off with 0.33 is equal to 2x squared over 1 minus x. So I'm just rewriting what we had. Spend more room here doing the algebra. So first thing, I want to get this denominator to the other side, so I'm going to multiply it over. So I have 0.33 times 1 minus x equals. I'll go ahead and distribute this squared here, so that squared has to go to the 2 and the x, so that's going to leave me with 4. 2 squared is 4, x squared. Now I'll distribute this guy, so 0.33 times 1 is 0.33, and then minus 0.33 times x. Still have 4x squared here. Now I want to get everything on the same side. I see that I have an x squared, this is a quadratic equation, so I want everything on one side, so I'm going to subtract this from both sides and add this to both sides. So I'll end up with 0 over here, and I'll still have 4x squared. And then I just want to put these in order, so plus 0.33x minus 0.33. And now what I have is a quadratic equation. And what do I use to solve? the quadratic formula. So our whole x equals negative b plus or minus square root of b squared minus 4ac. Put the whole thing over 2a. So look up your quadratic formula. I don't have it on here because it takes forever to write out, but we can go ahead and plug it in. So we know x is going to be equal to negative b, so negative 0.33, plus or minus the square root of, oops, sorry, my cat was trying to get involved. All right, square root of b squared, so that's going to be 0.33 squared, minus 4ac, so 4, and then a is 4, right? We have a, b, and c here. And c is negative 0.33. Don't forget about these negatives. They'll get you every time. So that whole thing's under the square root, and that's over 2a. So 2 times a, which is 4. So I got to plug this into my calculator. I'm going to have to do it twice because of this plus and minus thing here. And I'm going to get two answers. One is 0.249, and one is negative 0.331. Again, because of that plus or minus. So I'll plug it in and get these two answers, but only one of them is going to apply, and it's pretty easy in this case to see which one. I can't have a negative concentration, so I'm going to ignore that one and just take this one. Sometimes you'll get two positive numbers, and in that case, you'll always throw out the bigger number, because one number will be so big that when you go back and plug it into your ICE table, which is what we're about to do, you'd end up with negative concentrations. So if you have two positive numbers, throw out the bigger one. If you have a positive and a negative, you throw out the negative. So now, after all this algebra, we've solved for x, and we ask ourselves, all right, why did I even want this information? So we need to go back and look at the problem. X is equal to 0.249. We say, all right, what was it even asking me? Consider this reaction. Ah, there we go. What are A and B at equilibrium? So we go back to our ICE table and we see, oh, okay, so I had those, but I had x's in there, and now I know that x is equal to 0.249. I'm just going to plug it in. So A is equal to, let's put it in here, A is equal to 1 minus 0.249. So A is going to be equal to 0.751. And then B is going to be equal to 2 times 0.249, because it was 2x. Ooh, running out of space here. So B is going to be equal to 0.498. There's a 9 in there. 498. All right, squeezing it in there. So sometimes I'll also just write it under my ICE table. So 1 minus 0.249 gives me 0.751, and 2 times 0.249 gives me 0.498. So now I have the equilibrium concentrations of A and B, which are what I wanted. The big things I recommend for these problems is after you fill out your ICE table, take a look. I know it's kind of a mess now, but see if it's like in scenario 1, I erased that, where you had a number in your equilibrium. If you ever have a number in this row, you should be able to solve for x directly and then plug it in. In this case, we didn't have a number. We had expressions with x. In that case, when you plug it in, you're going to have to do all this algebra down here at the bottom and sometimes pull out the quadratic formula. Also, remember to keep track of what the problem is asking you to do. After you do all this work and solve for x, you're not done. It usually wants the equilibrium concentrations, so you're going to have to go back and plug x back into this last equilibrium row. We don't really have to worry about the rest of the ICE table because we didn't care about the change, anything like that. We just need to plug it into this equilibrium row to get these concentrations.